GameSide.com. GameSide.com.
Ahoy, mateys! Welcome aboard the learning ship. Today's lesson, weighted graphs. Let's solve some routing problems that involve money. Where there is a cost for using an edge, moving from one vertex to another, obvious costs, like the airline example. A flight is canceled and the airline needs to move 200 passengers to various destinations for the lowest cost. Time is money. Car/phone GPS wants to route you for the lowest time cost. Load balancing. Computer networks want to move data on the least used segments. The numbers on the edges indicate weight or cost to travel an edge. It costs 5 to move from edge A to E. This edge right there. Could be $5, could be 5 minutes, could be 5% bandwidth used. The goal of many graph algorithms is to find the hidden tree within the graph. A graph differs from a tree because it has cycles or redundant edges. When you eliminate those edges, voila, a tree emerges. Here are examples with 2 edges removed. Here's the original graph with the weights on the edges. If I remove a couple of edges, this one here and this one here, you can see the tree emerges. Here's the same graph with a couple of different edges removed. I removed this edge, and look, it looks exactly like a tree. This is a tree within the graph number 2. Both of these are the same nodes, or vertices, but I removed a couple of edges to get rid of the redundancy, to get rid of the cycles, and what do you have? A tree. Tree within a graph number 1 and tree within a graph number 2. A directed weighted graph adds an arrow to each edge and indicates it can only be traveled like a one-way street. The airline problem is a directed weighted graph. Airplanes follow schedules. At 8 a.m., a plane goes from airport A to airport B. That's directed. If it is canceled, only looking for planes that are traveling from A to X with a connection X to B. That is directed. Trucking/shipping seems two-way. After all, roads are two ways. But it is also directed. There are 6 trucks in a fleet. On Monday, they will travel A to B, A to C, A to D, C to B, C to E, and E to A. On Tuesday, a new directed graph will be needed. Trucks can only travel in one direction on the same day. An example of a truly undirected graph is a computer network, where data can travel from A to B at pretty much the same time it travels from B to A. We will look at 2 graph/routing algorithms in this lesson. Minimum spanning trees with weighted graphs. Dijkstra's algorithm, the shortest path on a directed weighted graph. There are many more graph algorithms out there, but we can't cover them all. These 2 will serve as examples of how graph/routing algorithms work. Minimum spanning tree, weighted graphs. This graph algorithm is very easy to relate to back-end software for video games. Large online games require players from all over the world to send messages/commands to computers called servers. It is the servers that run the game and send messages and commands back to the players. When more players are added to the game, more servers are needed. Since players in the same game may be connected to different servers, a lot of networking traffic occurs between servers. This algorithm allows load balancing, so busy network segments don't overload and slow the game's overall response time. Minimum spanning tree. Load balancing means you want to send data on the least used segments of the network. Just like freeway traffic, you want to avoid crowded roads that move slow. The weights listed on the graphs are the current used portion of the connection. So a 15 means 15% used bandwidth, and you want to utilize that segment. 90 means 90% used, and you want to avoid that segment. If it's 90% used, it's crowded, and you want to avoid it. Players continually log on and off, so we want to periodically look at network traffic and update routing tables to use the least used segments. Here is our graph. Start at vertex A and add it to the tree. The red circle around A indicates the vertex is done and we should place edges from this vertex into the priority queue. The priority queue is a min heap. Highest priority is given to the lowest cost edge, so AC10 is at the front of the queue. Vertex A is now done. There's no reason to cycle back to vertex A. The red circle indicates do not find a path back to A. Very important. Pick the cheapest edge, add that edge slash vertex to the tree. As you can see, C is the cheapest edge out of A. This one costs 10, this one costs 20, and this one costs 90. I'm going to pick 10 as the cheapest edge. At vertex C, add it to the tree. The red circle C indicates the vertex is done and we should place edges from this vertex into the priority queue. Into the priority queue, CF25 and CF80 are added in red because they are new edges added to the priority queue. AB20 and AD90 are in black to signal that they are existing edges or old edges that are already in the queue. Vertex C is now done. There's no reason to cycle back to vertex C. C has a red circle around it to indicate it's done and we should not come back to C. Important. Pick the cheapest edge. Add that edge or vertex to the tree. As you can see from the priority queue, AB20 is the cheapest single edge out of any visited vertex. At vertex B, add it to the tree. The red circle B indicates the vertex is done and we should place edges from this vertex in the priority queue. The red circle indicates B is done. In the priority queue, BE10 was added in red because it is a new edge. CF25, CE80, and AD90 are in black to signal they are older edges that have already existed in the priority queue. Vertex B is done. There's no reason to cycle back to B. It's important to pick the cheapest edge. Add that edge slash vertex to the tree. E is the cheapest. Edges indicates the edges of the tree. Here is a list of edges that were added to make up the tree. AC10, this edge right here, and AB20 are the current edges in the tree. Add vertex E added to the tree. The red circle indicates this vertex is done and we should place edges from this vertex into the priority queue. In the priority queue, EF40 was added in red because it is a new edge. CF25 and AD90 are in black to signal they are older edges that already existed in the queue. CE80 was removed because E is done. This edge used to be in the priority queue. It's taken out because now that E is in the tree, we don't need to use that route. EC80 was never put into the queue because C is done. Never add a cycle to the tree. It's important to pick the next cheapest edge, and the next cheapest edge that we can reach a vertex with is CF25. At vertex F, add it to the tree. The red circle F indicates this vertex is done, and we should place edges from this vertex into the priority queue. In the priority queue, FD45 was added in red because it is a new edge added to the queue. AD90 is in black to signal it is old or existing in the queue. Why are there only D edges in the priority queue? Because D is the only vertex we haven't visited yet. We remove edges back to existing vertices in the tree. EF40 was removed because F is done. FC25 was never put in the queue because C is done. Never add a cycle to the tree. Important to pick the only edge left, which is D. Also look at our list of edges. AC10, AB20, BE10, CF25. These are all the edges that we use to add a new vertex to the tree. At vertex D, add it to the tree. The red circle D indicates this vertex is done. No more vertices left. No more edges into the priority queue. In the priority queue, FD45 was removed and is listed in the edges below. AD90 was removed because D is done. The algorithm is done. All vertices are in the minimum spanning tree. The fewest number of edges to reach all the vertices is listed in edges. Here are the edges we use to add each vertex into the tree. Notice how busy edges like AD90 are not in this list. CE80 is not in this list. We're using the edges that are cheapest. You always pick the lowest cost edge when adding a new vertex in the tree. To highlight the minimum spanning tree with weighted graphs, the unused edges are blocked out. What this tells us is when A needs to move data to another server, follow these paths: AB, AC, ACFD, ABE, ACF, to avoid the most congested network segments. Notice how we're using the 10% and the 20% edges, and we're avoiding the edges that had 90% or 80% capacity. Use the least travel segments. This is the root of our minimum spanning tree, and this highlights the paths we want to take to the various parts of the graph. Let's do it again, starting from C. Let's do the minimum spanning tree with weighted graphs algorithm all over again, but this time start at vertex C and add it to the tree. The red circle indicates the vertex is done, and we should place edges from this vertex into the priority queue. The priority queue is a min heap. Highest priority is given to the lowest cost edges, so CA10 is at the front of this queue. CF25 and CE80, all the edges we can reach from C, they're in the priority queue with lowest used percentage at the front of the queue. Vertex C is done. There's no reason to cycle back to C. Important to pick the cheapest edge. Add that edge/vertex to the tree. A is the cheapest edge we can take. Let's add it to the tree. Add vertex A, adding it to the tree. The red circle A indicates this vertex is done. We should place edges from this vertex into the priority queue. In the priority queue, you can see AB20 and AD90 are added in red because those are the new edges we added when A was put in the tree. CF25 and CE80 are in black to signal they are older edges that existed in the priority queue. Vertex A is done. There's no reason to cycle back to vertex A. It's important to pick the cheapest edge. Add that edge/vertex to the tree, and B is the next cheapest edge we can reach from A or C. Add vertex B. Let's add it to the tree. The red circle B indicates the vertex is done, and we should place edges from this vertex into the priority queue. In the priority queue, BE10 was added in red because it's new. CF25, CE80, AD90 are in black to signal they are older existing edges that were already in the priority queue. Vertex B is done. There's no reason to cycle back to B. It's important to pick the cheapest edge. Add that edge/vertex to the tree. E is the next cheapest edge we can take to add something that wasn't in the tree to the tree. Notice the edges list. It indicates the edges of the tree. These are the edges used to build the minimum spanning tree. CA10 was an edge to add A to the tree. AB20 was an edge to add B to the tree. And BE10 is going to be added to this list to add E to the tree. Add vertex E, add it to the tree. The red circle E indicates the vertex is done, and we should place edges from this vertex into the priority queue. In the priority queue, EF40 was added in red because it's new. CF25, AD90 are in black to signal they are older edges that already existed in the priority queue. Notice CE80 was removed because E is now done. We don't need this edge in our priority queue anymore because it goes to a vertex we've already been to. EC80, this edge, was never put in the queue because C is done. Never add a cycle to the tree. It's important to pick the cheapest edge, and the next cheapest edge to a vertex we have not been to is EF40. Let's add F next. At vertex F, add it to the tree. The red circle F indicates this vertex is done, and we should place edges from this vertex into the priority queue. In the priority queue, FD45 was added in red because it's the new edge added to the queue because F is now in the tree. AD90 is in black to signal it's old. Why only D edges in the priority queue? Because D is the only vertex we haven't visited yet. EF40 was removed from the priority queue because F is done. FC25 was never put in the queue because C is done. Never add a cycle to the minimum spanning tree. It's important to pick the only edge left, and that is D. At vertex D, let's add it to the tree. The red circle D indicates the vertex is done. No more vertices left, no more edges in the priority queue. In the priority queue, FT45 was removed and is listed in the edges list. AD90 was removed from the priority queue because D is done. The algorithm is done. All vertices are in the minimum spanning tree. The fewest number of edges to reach all vertices is listed in the edges, right there. This is all the edges we used to build our minimum spanning tree. CA10 was used. AB20 was used. BE10 was used. CF25 was used. And finally, FD45 was used. Notice that busy edges like AD90 and CE80 are not in the minimum spanning tree, and they are not in our list of edges to use. To highlight the minimum spanning tree with weighted graphs, the unused edges are blocked out. What this tells us is when C needs to move data to another server, follow these paths: CA, CAB, CFD, CABE, and finally CF. This avoids the most congested network segments. Use the 10% used edges. Use the 20% used edges. Avoid the edges that are 80% used. Avoid the edges that are 90% used. C is the root of our minimum spanning tree, and this is the list of preferred edges to use when routing data from C. I know load balancing does not seem like an exciting aspect of programming online video games, but the success or failure of an online game hinges on responsive gameplay. The system must quickly react to players from all over the world. As more and more players sign on to your game, which is a good thing, do you want the game to slow down due to network bottlenecks? A popular game could have hundreds, even thousands of servers, all needing to communicate on a fast network. Making sure you route data on the least used edges of your network is one way to keep your game fast, responsive, and fun to play. Dijkstra's algorithm. The shortest path problem. Directed weighted graphs. Edgar Dijkstra, 1959. Find the shortest path from a starting vertex to all other vertices in a directed weighted graph. Graphing algorithms can be used in a variety of front-end video game scenarios, from a sim-style game establishing settlements, vertices, and roads, edges, to a war game where an army needs to create outposts, vertices, and supply lines, edges. In both cases, it's extremely important to do it at the lowest possible cost, and that's precisely what Dijkstra's algorithm does. Dijkstra's algorithm is all about money and getting the most bang for your buck. Dijkstra's algorithm. Central Command has ordered your battle group to establish 6 outposts in your sector, starting from Outpost Alpha, or A. Intel has provided damage estimates with 1 being low cost and 10 being high cost for each edge/battle needed to secure a new outpost. A directed graph, due to geography/enemy defenses, edges like A to B are deemed too difficult to attempt. Example, B is on high ground. Find the shortest path, the smallest battle damage needed to establish all 6 outposts. Use 999 to indicate infinity or no path possible. Here is our graph. We're starting in vertex A, and our estimates are it'll take 5 battle damage points to get to C. It'll take 9 battle damage points to get to D. There is no arrow from A to B. B is on high ground. You don't want to fight uphill. Start at vertex A and add it to the tree. The red circle indicates this vertex A is done, and we should place edges from this vertex into the shortest path array. In the array, let's use 999 to indicate infinity or no path. Currently, we do not have a path to E, so we list it as 999. Currently, we do not have a path to B, so we list it as 999. In red, we update the array with the vertices we can reach from A. We can go from A to C for a cost of 5, so we'll list a cost of 5 in our array and replace the 999. We can reach A to D for a cost of 9, so we'll update in red a cost of 9 to reach D and replace the 999. Vertex A is now done. There's no reason to cycle back to A. It's important to pick the cheapest path, not the edge, but the cheapest path. Add that edge/vertex to the tree. At this point, C is the cheapest path we can travel. We're not looking at an edge, but the entire path to get somewhere. And the cheapest path we can follow is A to C. C is next. Outpost or vertex C is captured, added to the tree. The red circle around C indicates it is done, and we should place edges from this vertex into the shortest path array. We're going to use green to indicate that the outpost or vertex is established. A was our starting point. It is in green because we don't need to find a path to A. We did take the edge from A to C. It is now in green. C is in the tree. We don't find another path back to C. In red, we update the path array with vertices we can reach from C. We can go from A to C to E for a cost of 13, so we'll add a total cost of 13 coming from C to get to E. Notice how the 999 was replaced. We don't need it anymore. We now have a path to E. Look at F. We have a cost of 7. It took us 5 to get to C and another 2 to get to F. So for a total cost of 7, coming from C, we can reach F. Once again, we'll replace the 999 cost to indicate we can reach F now for a cost of 7. At this point, it's important to pick the cheapest path, the total path. Add that edge/vertex to the tree. F is the cheapest path listed in the array to a place we haven't been yet. F is cheapest, add it next to the tree. The total cost ACF for 7 is cheaper than the AD9 that we have right there and the ACE13 that we have right there. Outpost/vertex F is captured, add it to the tree. F is now in our tree. Currently A, C, and F are done. We found the cheapest path and it's shown in green. Here's the cheapest cost to get to F, the cheapest cost to get to C, and of course we started in A. For DE, there is a cost, but it may not be the cheapest. Those prices are shown in black. We have a cost of 9 to get to D. We have a cost of 13 to get to E. Per the graph, B has an infinity cost of 999 because it does not have a path until E is captured. The path ACFD for 11, 5 plus 2 plus 4 is rejected. AD9 is less. What the heck am I talking about there? Once we add F to the tree, We could calculate a cost to get to D by adding 4. But 5 plus 2 plus 4 is 11, and we are not going to replace a cost of 9, A to D, with a cost of 11. Let's reject this new path to D. Does everyone see that? It's a little tricky. We already have in our array this path, A to D. We're not sure if it's the cheapest, but when we see this path, A, C, F, D, that is a new path, but it's not cheaper than the old path, so we'll keep the old cost 9 and reject the new cost 11. Important to pick the cheapest path, add that edge or vertex to the tree. D is the next cheapest path in this array. The total cost AD9 is much cheaper than ACE for 13. Note, higher edge costs, we don't care. It's the entire path that we're looking at. What is the total cost to get to D versus the total cost to get to E? 9 is less than 13. Outpost or vertex D is captured. Let's add it to the tree. Currently, A, C, F, and D are done. They're all circled in red. These outposts have been captured. Their cost is shown in green down in the shortest path array. We do not need to find another path to these vertices. Critical step. Each time a new vertex is added, find all the routes to the vertices not in the tree and update the shortest path array. Since D does not have an edge to E or B, there's nothing to update. We can't get to B. We cannot get to E. There's nothing to change in this array at this point. If a DB6 existed, 15D would have replaced B's 999A. If a DE6 existed, 15D does not replace E's 13C. Important, pick the cheapest path. Add that edge/vertex to the tree. At this point, the cheapest thing we can reach that we have not already been to is E for the cost of 13. Outpost/vertex E is captured. We've added E to the tree. Critical step. Each time a new vertex is added, find all the routes to the vertices not in the tree and update the shortest path array. Since E has an edge to B, replace the current cost of B, which is 99A, with the new cost of 16E. What did we just do? When we added E to the tree, we found this new path to B. That new path cost us 5 plus 8 plus 3, or a total of 16 to get to B. Well, 16 is a whole lot cheaper than 999, so 16 replaces our path to B. We use 999 as infinity because any new route will be less than 999. When a new route is not less than the existing path, we reject it. But when the new route is cheaper than the existing path, we replace the old cost. It's important to pick the cheapest path. Add that edge or vertex to the tree. We now have a path to B and a cost of 16. Let's add B to the tree. Outpost or vertex B has been captured. Add it to the tree. Mission accomplished. Starting from outpost/vertex A or alpha, the battle group has captured and established 6 vertices for the lowest cost. Important for the shortest path. Learn to read the array backwards. Under B is listed 16E. The total cost for all segments to reach B was 16. How did we get to B? Well, if you look closely, we went from E to B. This E indicates we went from E to B. Looking at E, how did we get to E? It's listed as 13C, so we went from C to E to B. Looking at C, how did we get there? It's listed as 5A. So what this is telling us is we went from A to C to E to B, and that's how we got to B. You've got to look at the array backward. Starting at B, we got there from E. From E, we got there from C. From C, we got there from A, back to the original starting point. That is the total path taken to capture outpost B. Read it backwards. ACF. How did we get to F? Looking at F, we got there from 7C. Going back to C, we got there from 5A. So reading backwards in the shortest path array, our path to F was A, C, F. To highlight the tree created by Dijkstra's algorithm, the unused edges are blocked out. This tells us, starting from A, follow these paths to establish the 6 vertices. To establish B, we started in A, we went to C, we went to E, and then we went to B. To get to C, we started in A and went directly to C. To get to D, we started in A and went directly to D. How did we get to E? We went A, C, E. How did we get to F? A, C, F. This shortest path tells you all those routes we took from A. Read the shortest path array backwards. The above list is in no particular order. Central Command decided which path/route gets executed next. Once we captured an outpost, we took the next cheapest path. Dijkstra's algorithm, the shortest path problem for a directed weighted graph. Let's do this whole thing over again, but this time start at vertex C and add it to the tree first. After the outposts are established, the enemy has pulled back and is attacking supply convoys moving between vertices. A directed weighted graph once again tells us the cost to move fuel, food, water, and ammunition between the outposts. Dijkstra's can be used to maintain a network. Enemies move, bridges are blown up, costs change over time. Starting from supply depot C, what is the cheapest cost to move materials to the other vertices? F is the cheapest path from C. Look at C. Right now, Intel is telling us it's a cost of 2 to move to F. That is the current cheapest path. Notice how I've updated the array. From C, it costs 8 to move to E. Update the cost to move to E to 8. I'll replace the 99C. From C to F, the cost is 2. So I'll remove the 999C and say update with a cost of 2. Let's go to F next. Outposts/vertex F is the cheapest. Let's add F to the tree. The red circle indicates the vertex is done and we should place the edges from this vertex into the shortest path array. Use green to indicate the outpost/vertex is done. Notice that C is green. That was our starting point. There's no need to move back to C. F has been added to the tree. It's in green. There's no reason to move back to F. In red, we update the path array with the vertices we can reach from F. From F, we can go to D for a total cost of 6. We started in C. It cost us 2 to get here, 4 to get there. We have a cost of 6 to reach D. So we will update the shortest path array in red. The cost of 6 from F replaces the 999C. It's important now to pick the cheapest path. Add that edge/vertex to the tree. D is the cheapest path. The total cost from C to F to D is 6, and that is certainly cheaper than CE's 8. D's path cost of 6 is cheaper than E's path cost of 8. D is the next outpost added to the tree. Outpost/vertex D is the cheapest. It's added to the tree. Currently, C, F, and D are done. We found the cheapest path shown in green. C is done, F is done, D is done. They're all listed in green. Remember, we started in C, so it has a cost of 999 or infinity. Critical step. Each time a new vertex is added, find all the routes to vertices not in the tree and update the shortest path array. Since D does not have an edge to A, E, or B, there's nothing to update in the array. Notice D. It has no outgoing routes. With no outgoing routes from D, there's nothing to update in the array. Now, what if it did have an outgoing route? What if there was an edge from D to B? If DB6 existed, 12D would have replaced B's 999A. What if DE6 existed? What if there was an edge from D to E for the cost of 6? Well, if that existed, 12D does not replace E's 8C. You only replace or update a number when you find a cheaper route. Important, pick the cheapest path, add that edge slash vertex to the tree. At this point, the cheapest path we have that's not already in the tree is E for the cost of 8. Outpost vertex E is the cheapest. Add it to the tree. Critical step. Each time a new vertex is added, find all routes to vertices not in the tree and update the shortest path array. Since E has an edge to B, replace the current cost of B, the 999C, with the new cost of 11E. 8 plus 3 cost 8 to get to E and another 3 to get to B. That's 11. That's a new cost that is cheaper than the existing cost. We use 999 as infinity because any new route will be less than 999. Root F is rejected. F is already in the tree, and 12 is greater than 2. What does that mean? We now have a route to F, C to E to F that costs 12. But F is already in the tree, so we'd never re-add it to the tree. And besides, we already have a cost of 2 to get to F, so we reject this route altogether. Important, pick the cheapest path. Add that edge or vertex to the tree. Right now in the tree, the cheapest cost we have is B for the cost of 11. Let's pick B next. Outpost slash vertex B is the cheapest. Add it to the tree. Critical step. Each time a new vertex is added, find all routes to vertices not in the tree and update the shortest path array. Since B has an edge to A, there it is, replace the current cost of A, the 999C, with the new cost of 17B. It cost us 8 plus 3 plus 6, or 17, to get to A. Use 999 as infinity because any new route will be less than 999. When a new route is not less than the existing path, reject it. Important to pick the cheapest path. Add that edge or vertex to the tree. At this point, A, of course, is the cheapest path because it's the only thing not in the tree. It has to be the cheapest. Outpost or vertex A is reached. Add A to the tree. Mission accomplished. Starting from outpost slash vertex C, or Charlie, found routes for moving supplies to 5 vertices for the lowest cost. Important for the shortest path. Learn to read it backwards. Under A is a 17B. Total cost for all segments to reach A is 17. How did we get to A? We got B to A. We took B to A. Looking at B, how did we get to B? There's an 11E under B, so we went from E to B to A. Looking at E, how did we get to E? There's an 8C listed under there. That tells us we went from C to E to B to A. That is the path taken to supply A from C. Learn to read the shortest path backwards. How do we get to D? D said we got there from F. How do we get to F? It says we got there from C. Reading that backwards, take C to F to D. That is your route from C to D. And we learn that by reading this array backwards. We got to D from F. We got to F from C. We're back to our starting vertex. To highlight the tree created by Dijkstra's algorithm, the unused edges were blocked out. This tells us, starting from C, follow these paths to supply all the vertices. Go from C, which is our root, our starting point, to E, to B, to A to get supplies to A. Starting from C, go to E to B to get supplies to B. Starting from C, go to F, D to get supplies to D. And then, of course, directly C to E and C to F to supply those two outposts. Read the shortest path array backwards. The above list is in no particular order. Central command decides which outposts get supplies next, and that path is executed. Know the differences between Dijkstra's algorithm and the minimum spanning tree algorithm. Dijkstra's is for directed weighted graphs. Minimum spanning trees are weighted only graphs. Dijkstra's requires a path array. Minimum spanning tree requires a priority queue. In Dijkstra's, we calculate the full path cost. In minimum spanning tree, we only look at the cost of a single edge. Know the similarities between Dijkstra's and minimum spanning tree. Mark visited vertices. That's the same for Dijkstra's and minimum spanning tree. Find the tree within the graph. That is the same for both algorithms. No cycles. Never go back to a vertex you've already visited. That is the same. And find a set of preferred edges. Both algorithms do that. Find the hidden tree within the graph.
Dijkstra.com.